It's really kind of wild when you think about it. How AI just seems to get what you mean. When you type it a prompt, like boom, a poem, a crazy picture, even helps you code that tricky function you've been avoiding. Almost like mind reading, right? And that's kind of what we're looking at today, peeling back the layers, like how do these AI models, the ones behind all these cool tools, how do they actually get our prompts?
Exactly. You use these tools, you see the amazing results, but it's kind of mysterious, right? What's going on in there?
Totally a black box.
So yeah, in this deep dive, we're going to shine a light into that box, trying to understand what's happening, at the core, the stuff that makes these models take our words and turn them into, well, everything they make. And is it the same process for text, pictures, videos? And how can we use all this, to write better prompts, to get better results, whether it's LLMs, image generators, even AI code editors?
Right. We've all been there.
Yeah.
Staring at the cursor, like, how do I freeze this? So that's the heart of it. How do these models take human language and make it into something they can actually use? Same steps for a summary, a weird landscape, a clip of a dog fetching.
And if you know the process, does it make your prompts better? Not just for language models, but for all sorts of generative AI.
Exactly.
To answer those questions, we went deep into the research, looked at how large language models are built, how they process information, the crazy techniques that turn text into visuals and movement, and of course, how to use tools like Cursor, Windsurf, and Klein to get the code you actually want. So ready to open the hood.
Let's do it. Let's
Okay.
start where a lot of folks start with AI. LLMs, large language models, the things behind chatbots. When you type in a prompt, what's the first thing to understand about how they make sense of it?
The key is this. LLMs are like super advanced next word predictors. They've been trained on these massive data sets of text and code. They're learning, essentially, how likely words are to appear in sequences. So when you give it a prompt, it's not understanding like a human, with meaning and all that. It's predicting the next word statistically based on the patterns it's seen.
So it's less reading my prompt and more like what word statistically follows this sequence of words.
Yeah, like autocomplete, but on a huge scale. And we usually interact with them in two main ways. First, there's instruction-based prompting. You just tell the model what you want it to do. Explain relativity simply, or write a poem about fall.
Straightforward, a command.
Right. Second is completion-based prompting. You give it a start, and it finishes the thought. Like, the best way to learn a language is, and the model goes from there, but it doesn't know when to stop. So you got to use things like stop sequences or clean up the output to keep it focused.
Interesting. So I hit enter on my prompt. What happens to those words inside the LLM? It's not
Okay.
reading letters like we do, right?
Right. There's a prep stage. First, the context window. It's how much of the recent conversation or prompt the LLM remembers at any given time. It's limited, varies between models, and it limits how long your prompts can be. There's even this lost in the middle thing where in a long input, models sometimes forget stuff in the middle but remember the beginning and end better. And then before it even really gets to your request, it does some cleanup, lowercase everything, standardizes punctuation, for consistency.
A little prompt scrubbing. Then what? What are these tokens everyone's talking about?
Tokenization. Super important. You're basically breaking down the prompt into smaller chunks. Could be a whole word, part of a word, even a single character. Depends on the method. LLMs don't work with raw text. They need numbers. So each unique token gets a numerical representation, an ID in the model's giant vocabulary.
So apple is one number, banana another.
Exactly. Now, there are different ways to do this tokenization. Word level. Each word is a token. Character level, each letter, punctuation mark, becomes a token. But a lot of the big LLMs now use subword techniques like byte-pair encoding, or BPE.
Byte parent coding. Sounds complicated.
It's actually pretty elegant. It starts with each byte, often a character, as a token. It looks at the training data, finds the most common pair of tokens, and merges them into one new token. It keeps doing this, finding pairs, merging, until it hits a certain vocabulary size. So common letter combinations, even short words, become their own tokens. Helps the model handle new words it hasn't seen before, breaks them down into familiar bits.
Clever way to handle the usual and unusual words.
Well,
So my prompt's a string of numbers now. What does the LLM do with that?
here's where the transformer architecture comes in. This is the big deal, the foundation for lots of advanced LLMs. It's a breakthrough because it solves some problems older designs had, like understanding how words far apart in a sentence connect and processing stuff in parallel. The heart of the transformer is the self-attention mechanism.
Self-attention. That sounds interesting.
Okay, let's break this down. Imagine the model's looking at a sentence in your prompt. Self-attention lets it weigh the importance of each word in relation to the others. For every word, it creates three vectors: a query, a key, and a value. Think of it this way. The query is the word asking, hey, what other words in this sentence are relevant to me? It compares itself to the other word's key vectors. This gives it an attention score for each other word, telling it how much to focus on them. These scores then adjust the value vectors of the other words, so you end up with a representation of that word that's informed by its context. The model's not just looking at each word individually, it's understanding the relationships between them in the whole prompt.
So not just reading in order, but understanding connections.
Right. And to make it even more powerful, you often have multi-head attention. It's like having many sets of these query, key, value things working at the same time. Each head can learn to focus on a different kind of relationship in the text, grammar, meaning, and so on. Combine the results from all the heads, and you get a much richer understanding. Finally, in decoder-only models, which are common for a lot of LLMs, the model uses this understanding to predict the next token in the sequence. And it does this again and again, token by token, to create its response.
Wow. That's a lot going on behind the scenes. Now, is this how image and video models interpret our prompts too? Or is it totally different?
It's a great question. While the goal is the same, translating your words into something the model can use, the techniques are pretty different. For images, it starts by turning your text prompt into visual features. This is usually done with NLP models, natural language processing, trained on a massive amount of images and their text descriptions. These models look at your prompt, figure out what objects you want, their qualities like color and size, actions, relationships. Like in LLMs, tokenization and word embeddings are super important. Those embeddings represent words as numbers, capturing their meaning and how they relate to other words.
So the text part is kind of similar.
The NLP is key to understanding what the prompt means, but instead of predicting a word, it's trying to create a visual representation. A big concept here is the latent space. Imagine it like a compressed, high-dimensional code for images. It captures the essential parts and variations of images more abstractly than just pixels. Text prompts often get mapped into this space, and then the image generation model could be a diffusion model, or a GAN decodes this code back into an actual image with pixels.
Diffusion models and GANs, those are the big names, right?
Yeah, they're the leading architectures now. Diffusion models, popular for making high-quality images, work by basically reversing a process. They learn to undo the gradual addition of noise to an image until it's just random static. When they're generating, they start with random noise and slowly remove it, guided by the prompt, which has been turned into that latent space code. It's like unblurring a super blurry image using a description. GANs, on the other hand, use two networks: a generator that tries to make realistic images from the prompt, often through that latent space, and a discriminator that tries to tell the difference between real images and the ones the generator made. They're trained in this back and forth game, the generator trying to fool the discriminator. And then there are variational autoencoders, or VAEs, that are often used to learn those compressed latent space representations that both diffusion models and GANs use.
That sounds pretty different from the step-by-step word prediction in LLMs. What about video generation? That seems even harder, having to handle visuals and motion.
You're right. Video models take the image techniques but add in the time dimension, not just individual frames, but a sequence, how they change over time. Early models struggled with keeping things consistent. You'd get this drift where stuff would subtly change in illogical ways.
So how do they deal with that time aspect now?
One way is to generate a keyframe, the first image, based on the prompt, and use that plus the prompt to guide the rest of the frames, paying attention to motion. Action words in the prompt are super important. Diffusion models are really good for video too. They learn to reverse the noising process on sequences of frames, guided by the text prompt. Architectures like the diffusion transformer or DIT, which powers models like Sora, are built for this. They capture those long-term dependencies that are crucial for consistent, realistic motion. There are other approaches, like models that learn motion patterns from tons of video data, and then apply those patterns to images made from a text prompt. Some even generate a low-res video first and then upscale it to higher quality.
So there's the text part, but the actual image and video generation is pretty different from LLMs.
Yeah.
What about tokenization? Do they use the same kind of tokenizers to break things down?
Another sharp question. The basic goal is the same: turn the input into numbers. But the techniques and the tokens themselves are very different.
Can you explain that?
Think about LLMs. They use things like BPE, breaking text into words, parts of words based on how common they are. But images, the input isn't text, it's pixels. So image tokenization is different. One common method is patch-based tokenization. You divide the image into a grid of squares, patches, and each patch is a token. These are often processed by vision transformer architectures, adapted from LLMs but designed for visuals. There are newer things too, like 1D tokenizers that try to turn a 2D image into a more compact 1D sequence of tokens. Instead of language units, we're dealing with visual units.
Makes sense. What about video with that extra time element?
For video, you've got both the spatial information within each frame and the temporal information across frames. Tokenization gets even more complex. You have techniques that capture both. Things like Omni-Tokenizer, Chord Talk, MagVIT-v2. These are spatial temporal tokenization approaches. They break a video into tokens that represent not just what's in each frame, but how things move and change over time.
It sounds like, while they all need numbers, the way they get there is tailored to the data. Text, image, or video.
Exactly. LLMs are about patterns in language, image and video models about visual features, movement dynamics. But there's a whole area of research on unified tokenization frameworks that could handle multiple modalities, text, images, video in one system. Pretty exciting.
Sounds like the future. So, knowing all this about prompts, what are the takeaways for us? How can we write better prompts for LLMs, image, video generators, even those AI code tools?
That's the real question, isn't it? Some basic best practices apply across the board. Clarity, specificity. The more precise you are, the better the model gets you. Give it context, background information, any limitations. Break down complex stuff into smaller tasks. Be clear about the output format you want: a list, a table, a paragraph of a specific length, code in a certain language. And remember, it's iterative. Try different phrases, refine based on what you get back.
Good general advice. What about techniques specific to LLMs?
For LLMs, there's a whole toolbox. Zero-shot prompting, where you give it a task with no examples. Few-shot prompting, where you do include a few examples to show the format and style you want. Chain of thought prompting, good for complex reasoning, where you guide the model to break the problem into steps. You can experiment with perspective prompts, asking it to take a certain viewpoint, using pseudocode-like syntax to give very precise instructions. Even assigning roles, like you're an experienced Python developer, to influence its tone and style. Managing the context window is key, too. Summarize large amounts of info or use techniques like retrieval augmented generation to focus its attention. When using few-shot, the quality and order of your examples matter a lot. Watch out for biases. Finally, be clear about the output format. Remember, model parameters, like temperature, affect how random and creative its responses are.
Tons of tools for LLMs. Now, for image and video, our sources didn't really give specific techniques like that. But based on how they work, can we infer some best practices?
Of course. Since they use NLP to translate text into visuals and motion, being really descriptive is key. Don't just name the objects, describe their qualities, color, size, texture, actions, camera angle, lighting, composition. Clear, unambiguous language helps the NLP model translate accurately into visual concepts for the generator. For video, be specific about motion, desired length, the relationship between frames. You're painting a picture with words for the AI to turn into reality.
Makes sense. More detail, better visuals. Now, what about code generation? AI IDEs and VS Code extensions like Contline, Cursor, Windsurf. Any unique techniques for those?
A lot of what we've discussed applies. Specificity, clarity, context like existing code or errors, desired output format, a function, a class, a snippet. Using positive constraints, saying what you want instead of what you don't want, tends to work better. Assigning a persona, like act as a senior developer, can impact the code style. Starting with leading words like write a function that helps guide the AI.
Specifics about tools like Cursor.
Cursor has a few ways to interact. Inline prompting, chat, and the composer for bigger stuff. The act mention is great. You can pull in context directly from your code, the web, docs. You can also define cursor rules to enforce certain code styles. When prompting, be clear about which code you mean, inline prompting, or give detailed instructions in the chat. The composer helps with larger tasks. Avoid being vague, asking for too much code at once, or not giving enough context. Rephrase if the results aren't what you want. And play with cursor settings. You can change the AI model, enable code base-wide context for better suggestions.
How about Windsurf?
Windsurf's big on natural language through its command palette. It has different modes: Cascade, Inline AI, Super Complete. Understand these, tailor your instructions accordingly. At mentions in Cascade can reference files, directories, give context. You can define memories and rules for consistency. Watch out for the AI rewriting code unintentionally or not following your instructions exactly. Experiment with Windsurf settings, choose the right Cascade mode, use its linter integration for quality code.
Lastly, Contline.
Cline is about conversation. And custom instructions in settings or a project-specific .cliners file. This lets you set project-wide standards. Prompt Cline in a clear, step-by-step way, provide context, use @var files and folders, techniques like setting constraints, asking it to explain its logic, even asking stupid questions to be really clear about edge cases, can work well. Avoid complex syntax, ambiguous instructions, check out Cline's settings for API provider, AI model, context window size.
So to wrap up our dive,
Yeah.
we saw how LLMs interpret prompts. Next token prediction, based on all those patterns they learned. Image and video models start with NLP, but then they translate into visual features, work in latent spaces, using things like diffusion models and GANs. And tokenization, it's crucial, but the way it's done is very different for text, images, and video.
And we've talked about a bunch of practical ways you can write better prompts for LLMs, image generators, video generators, even those AI code tools. Knowing this stuff, even at a high level, can really make a difference.
Yeah.
Absolutely. This isn't just about how they work in theory, it's about using them better, more creatively. So think about how all this can help you get more out of AI. Experiment, try the techniques we talked about, and you might be surprised at the results.
I agree. Thanks for joining us today for this deep dive.
And stay tuned for more deep dives into the world of tech and beyond.